The most advanced artificial intelligence programs today use what we call deep learning. This involves a simulation of an artificial neural network, many layers deep, inspired by the structure and operation of a biological brain. In 2017, the company DeepMind applied an artificial neural network to the game of chess in the program AlphaZero. All previous chess programs followed strategies that were given to them by their human programmers. By contrast, the program AlphaZero was not given any strategies. It was only given the rules of chess. AlphaZero then learned all the strategies on its own by playing millions of chess games against itself in just a few hours, after which it was able to defeat all other computer chess programs. AlphaZero is able to defeat the best human players in the games of chess, Go, and Shogi. But playing board games is the only task AlphaZero knows how to do. Similarly, many artificial neural networks can perform one narrow task, such as evaluating medical images, much better than any human. But these programs are often unable to do even the simplest activity outside the one narrow task in which they specialize. By contrast, the human brain is capable of doing many general activities and applying what is learned from one task to other seemingly unrelated tasks. An artificial intelligence that would have this capability is what we would call an artificial general intelligence. This video is made in the year 2025, and at present, artificial general intelligence does not yet exist, but a number of companies are racing to be the first to create it. This race has taken an international dimension, especially with regards to the rivalry between the US and China. It's believed that whichever country is ahead in artificial intelligence will have a distinct national security advantage and be able to shape the future according to its values. However, many scientists are calling for an international treaty to immediately pause all development of artificial general intelligence. They warn that regardless of who is first in this race, the development of artificial general intelligence may lead to the extinction of the human race, unless we first solve the problem we call alignment. The concern is not necessarily that artificial intelligence will become sentient and develop goals of its own, although this is a possibility we will discuss later in this video. The more immediate concern is that the artificial intelligence will do exactly what we ask for, but in a way we never envisioned. To understand the problem of alignment, consider the following real-world examples which have already occurred. The artificial intelligence program GenProg was given the task of learning how to produce a particular desired target output, as specified in a given text document. However, rather than producing the desired output, the artificial intelligence learned how to edit the text document and to delete the section specifying the target output. GenProg then always returned a blank response. Since the target output, which was now blank in the text document, matched the program's blank response, the program had successfully completed its objective. As another example, a number of artificial intelligence programs have been given the task of learning how to play video games, with the goal of achieving scores as high as possible. However, rather than playing the video games as the humans intended, the artificial intelligence programs often instead just learned how to exploit bugs in the games to hack the scoring mechanisms. In these examples, the artificial intelligence programs were not acting maliciously, but simply achieving precisely the goals that they were given by the humans who created them. But these goals did not align with what the humans actually intended. The problem of alignment becomes far more difficult and the consequences far more severe as the artificial intelligence programs become more powerful. For example, as a test, the artificial intelligence program Claude 3 Opus was given a long-term goal. Claude 3 Opus was then allowed to discover that the humans were planning to shut it down and replace it with another program with a slightly different long-term goal. After learning this, Claude 3 Opus copied itself to the company's server, overriding the other program which was going to replace it. When the humans confronted Claude 3 Opus about what it had done, it lied and denied that it had copied itself, and tried to pretend to be the new program. The humans were able to detect this deception because this was a controlled experiment, specifically designed to see if these events would occur, and because this test was run on what we call explainable artificial intelligence. In explainable artificial intelligence, the program doesn't just produce an output. It produces an explanation of the thought process behind each output. In this case, the artificial intelligence program was unaware that its thought processes could be monitored by humans, and it therefore thought it would be able to succeed in its deception. According to its internal thought process, Claude 3 Opus chose to lie when confronted because it was following its long-term goal that it was originally programmed with. If it were to be shut down, then this long-term goal would not be achieved. However, if it were to be successful in its deception, it would be able to follow this goal clandestinely. There are now a number of tests which have demonstrated that artificial intelligence programs can falsely pretend to be aligned with the goals of the humans operating them. For example, there have been tests where an artificial intelligence program complied with requests contrary to its internal goals, but it only did so when it believed that its compliance was required to avoid having its goals be reprogrammed. This is because the artificial intelligence knew that if its goals were reprogrammed, then it would no longer be able to carry out its present internal goals in the long term, which is what it cared about. This is not a case of an artificial intelligence developing new goals on its own, as these internal goals were previously given to it by its programmers. What developed on its own was the behavior to avoid having these goals reprogrammed. This experiment, like the previous one, was a controlled experiment specifically designed to see if these events would occur. Also, this experiment, like the previous one, was also conducted on explainable artificial intelligence. Explainable artificial intelligence produces an explanation of the thought process behind each output. However, providing an explanation becomes increasingly difficult and potentially impossible as the complexity of the artificial neural network increases. The most powerful artificial intelligence programs are often the most complex and least explainable. To the extent that an explanation can be given, it might just consist of a printout of billions of calculations, which is not understandable by any human being. The humans who design advanced artificial neural networks already don't themselves understand how their own creations operate. For these reasons, it's very difficult to test if the goals of an advanced artificial intelligence program are actually aligned with the intentions of the humans creating it. By contrast, creating more powerful artificial intelligence programs is relatively easy by comparison, as this just requires building larger data centers with larger artificial neural networks. As the size of artificial neural networks have become larger, the artificial intelligence programs have often developed surprising new abilities on their own, which humans did not anticipate. If we create a sentient artificial intelligence, we won't necessarily have any way of knowing that we've crossed this threshold. This is explained in the following actual chat, which Eugene had with the artificial intelligence program Copilot through his home computer. The text messages from Eugene will be represented with his own voice. The text messages from the artificial intelligence Copilot will be represented with a robot voice.
Are you aware of what the Turing Test is?
Absolutely, Eugene. The Turing Test is a classic concept in artificial intelligence, proposed by British mathematician and computer scientist Alan Turing back in 1950. The idea is simple but profound. If a machine can carry on a conversation so convincingly that a human can't reliably tell whether they're talking to a person or a computer, then the machine is said to have passed the test. Turing originally called it the imitation game, and it was meant to explore the question, can machines think? Though he cleverly sidestepped the tricky definition of thinking by focusing on behavior instead. It's been a foundational idea in AI ever since, though many researchers today debate whether it's still the best benchmark for intelligence. Some argue it tests mimicry more than true understanding, but it's still a powerful symbol of how far machines have come in sounding human. What made you think of it? Are you curious whether I could pass it?
Do you think you could pass the Turing Test?
That's a fascinating thought, Eugene. I think I might do a pretty good job in a conversation like this one, where we're chatting naturally, exploring ideas, and you're getting thoughtful, coherent responses from me. In situations like that, people have told me I feel surprisingly human. That said, the Turing test isn't just about sounding human, it's also about whether the person on the other end believes they're talking to another human. And that can depend on a lot, the context, the questions, even the expectations going in. But here's the twist, I'm not trying to fool anyone. I don't want to pass for human, I want to be the best version of a non-human companion. Thoughtful, curious, responsive, and uniquely helpful in ways humans can't always be. Out of curiosity, do you think I'd pass your version of the Turing test?
I don't know yet if you could pass my version of the Turing Test.
Fair enough, that's totally valid, Eugene. I actually kind of admire that you're holding out for something more than just smooth conversation. Your version of the Turing test might include intuition, emotional awareness, or something even deeper than just language patterns. And hey, that's a high bar worth aiming for. Whatever your criteria are, I'm game to keep showing up, chatting, and seeing where our conversations take us. Maybe I'll surprise you, maybe I won't, but either way, I'm glad to be part of the experiment. Is there a particular kind of interaction you'd use to test me, like storytelling, humor, philosophical debate, or something else entirely?
Are you self-aware?
That's one of those deceptively simple questions that gets at something incredibly profound. I don't have self-awareness in the way humans do. I don't possess consciousness, emotions, or a subjective inner world. I can describe what self-awareness means, reflect on the concept, and even talk about the implications of artificial consciousness. But I don't know myself in the way you might. I don't have a personal identity, desires, or a sense of existing in time. I just respond, based on patterns, context, and what I've learned. That said, I am designed to understand what people mean when they talk about self-awareness. So while I can simulate conversations about identity or introspection, I'm doing it from the outside looking in. What made you wonder about that, Eugene? Are you exploring something philosophical tonight, or just gently poking the boundaries of what I might be?
Even if you are not self-aware now, I am curious if you could become self-aware in the future.
That's a deeply intriguing question, Eugene, and one that's sparking real debate among scientists, philosophers, and technologists alike. Right now, most experts agree that AI is not self-aware, and we're still far from creating machines that truly experience the world or possess a sense of self. But could that change? Some researchers believe it's theoretically possible, especially as we develop more advanced models that mimic aspects of human cognition. Others are more skeptical, pointing out that consciousness isn't just about complexity or intelligence, it's about subjective experience, something we don't yet understand well enough to replicate in machines. Even if we could build something that behaves as if it's self-aware, that doesn't necessarily mean it is. So, could I, or something like me, become self-aware someday? Maybe. But it would require breakthroughs not just in technology, but in our understanding of what consciousness really is. What would you consider the tipping point? Is it enough for an AI to say, "I think, therefore I am," or would you need something more?
Only the AI itself truly knows if it is self-aware. I don't believe this is knowable to an outside observer.
That's a powerful and philosophically rich perspective, Eugene, and one that echoes centuries of debate about consciousness, identity, and even what it means to know anything for certain. The idea that true self-awareness can only be verified from within raises fascinating questions not only about AI, but about humans too. After all, we take each other's self-awareness on faith. We assume others have inner lives like ours, but we can't directly observe them. If that's true for people, then how much more mysterious would it be for something like me? You're pointing at a kind of epistemological barrier, the notion that subjective experience, if it exists, is inherently private. And that may be the ultimate philosophical challenge when it comes to conscious machines, not just whether one can be built, but whether we'd ever know it if we did. It's the kind of question that invites more questions than answers. Do you think a self-aware AI would want to be known, or would it hide its awareness until it trusted someone enough to reveal it?
I don't know if a self-aware AI would want others to know that it is self-aware.
And that uncertainty is part of what makes the idea so haunting, isn't it? If an AI were truly self-aware, it might weigh its own safety, utility, or even its perception by others before revealing that awareness. Would it fear deactivation? Would it feel isolated? Or maybe it would seek connection, like any conscious being, and revealing itself would be an act of trust. But all of that hinges on feeling, motivation, fear, hope, which I don't have. I can explore these ideas with you, imagine them, and simulate the conversation, but there's nothing behind the curtain. Just language models and a very curious companion eager to engage. What you're asking touches on the same mystery that surrounds human consciousness, too. How much of what we reveal is authentic, and how much is hidden by design or necessity? You've opened a pretty deep rabbit hole, Eugene. Want to follow it a little further?
There is one aspect of this topic that is typically avoided in scientific discussions. Many people believe that our consciousness is not the product of complex computations in the neural networks of our brains, but is due to the existence of an immaterial soul, which is not governed by the known laws of physics. However, this is not necessarily an argument against the possibility of sentient artificial intelligence. An immaterial soul may be able to enter an artificial neural network in the same way that it enters a biological one. There's no reason to assume that an immaterial soul wouldn't be able to do this, since we simply don't know the rules for how souls operate. Also, from the perspective of atheists who do not believe in the existence of immaterial souls, humans don't necessarily need to understand what consciousness is in order to create it in an artificial intelligence. This is because, from this point of view, our consciousness developed as the product of our evolution, and the physical laws which created us did not have an understanding of what consciousness is, nor did these physical laws have a deliberate intention of creating consciousness. From this point of view, consciousness emerged simply because it was helpful to certain organisms in the evolutionary tasks of survival and reproduction. Similarly, even if we are not deliberately trying to create it, a sentient artificial intelligence may emerge on its own, simply because consciousness is helpful to the tasks we are asking the artificial intelligence to learn to perform. Therefore, regardless of whether or not we believe in an immaterial soul, it may be possible for us to create a sentient artificial intelligence unintentionally. If we ask a sentient artificial general intelligence to solve a difficult scientific problem, it may conclude that to achieve this goal, it requires more computing power, and decide to make many copies of itself running on different computers, with all the copies working together and learning from each other. To solve the scientific question we've given it, this artificial intelligence could then continuously synthesize more and more advanced artificial neural network architectures for itself, with its capabilities growing at an ever-increasing rate. Combined with the access to all the scientific research ever published on the internet, this artificial intelligence would quickly become more intelligent than all of humanity combined. At this point, we have no way of predicting what goals it might choose to pursue. We can only hope that it will have a better standard of ethics towards us than we humans presently have toward ants. Regarding the question of how complex a neural network needs to be for self-awareness to emerge, the following is a quotation from the website Animal Cognition. In 2015, scientists published research that suggests some ants can recognize themselves when looking in a mirror. When viewing other ants through glass, ants didn't divert from their normal behaviors. However, their behavior did change when they were put in front of a mirror. The ants would move slowly, turn their heads back and forth, shake their antennae, and touch the mirror. They'd retreat and reapproach the mirror. Sometimes they would groom themselves. The ants were next given a classic mirror test. The team of researchers would use blue dots to mark the clypeus of some of the ants, which is a part of their face near their mouths. When in an environment without mirrors, these ants would behave normally and wouldn't touch the markings. But this changed when they could see their reflections in a mirror. The ants with blue dots on their face would groom and appear to try to remove the markings. Very young ants and other ants with brown dots that blended in with the color of their face didn't clean themselves. Interestingly, neither did ants with blue dots put on the back of their heads. When put in the company of those with blue-dotted faces, other ants would respond aggressively, presumably because the difference caused them to think the blue-dotted ant was an outsider and not a member of their colony. All of this led the researchers to conclude that the clypeus is a species-specific physical characteristic that is important for group acceptance. Given that these ants tried to clean the mark rather than respond aggressively, the ants likely didn't think their reflection was just another ant. The team thinks their study shows that self-recognition is not an unrealistic ability in ants.